Today is December 14th, 2011. This is the 8.2 lecture. Okay. Oh, I'm sorry. We're not going to focus on D. We're focusing on E. We're looking at the estimation for population proportions. In other words, we're going to be looking at particular confidence intervals having to do with proportions. Now, at the end of this, we're actually going to be working with numbers, so it's going to feel more like a math class again, and we're going to be able to construct and interpret a confidence interval for a population proportion. We're also going to talk about how can we determine how big of a sample size you need in order to get a margin of error that's acceptable to you. And then lastly, we're going to describe how the margin of error of confidence interval changes with sample size and changes with the confidence level. All right? We're not doing that. All right, let's go to the numbers. Okay, let's say we had something that we were sampling. In the course of this example, they have red beads. You've got a big thing of beads. Some of them are red. And how big is this thing that's got beads in it? Oh, it's this big and this big. It's huge. And I'm going to give you a choice. I want to find out what proportion of those beads in this huge bin are red. You may choose to, 1, empty out the thing, separate the red beads from the other colored beads, count them all by hand, and then give me the proportion. I'm going to call that barrel of beads a population. And I want to find out what proportion are red. Lots and lots of beads in there. Do you want to do all of them? Well, it depends. Do I need you to be 100% accurate? No, I just want to get a sense of what proportion are red beads. What if you did a sample instead? What if you scooped up a bunch of beads, got 144 beads, and 107 of them happened to be red? Does that give you the ability to have some insight about what proportion in the population is red beads? That's the idea, again, of sampling instead of doing a population census. We found that if we had 107 beads out of 144 drawn, that about 42.6% of those beads were red. Oh, I'm sorry, 107 beads, and there was 144 beads of other color. Add those two to get 251. Sorry, my mistake. Now, 42.6. P hat is equal to 0.426. We have words from the previous lecture that describe that number. We call that number a statistic because it comes from a sample. We call it an estimator or a point estimator because it's our estimate of what's going on at the population level. And of all the things we think, we don't think that is exactly the right value for the population proportion, but we think it's a reasonable guess. It's a starting point. I would like to use a formula here. I would like to use the formula that we talked about in the previous lecture, which is, and I'll write it out one more time, that the confidence interval is equal to p hat plus or minus some critical value multiplied by the standard deviation. Well, I won't write standard deviation, I'll write square root of p hat 1 minus p hat all over n. The standard deviation of the sampling distribution. We ended last lecture though saying that formula doesn't come for free. You've got to have conditions. The three conditions again were unbiased, normal, and independent. independent. So, how would we say, is our sample unbiased? Well, were the beads really well mixed inside of our barrel? If they were, and we grabbed out without looking in them, do you think we would say that's a random, unbiased sample? That seems pretty reasonable. Second question. Let's go with independence. Independence only comes if the population is substantially larger than our sample, at least 10 times the sample size. Did I describe a really big barrel of beads? Do you think 251 of them is less than 10% of the population in my description? Okay, let's say that one is also good. Last one. Last question. Do we think that using this method we would get at least 10 successes or 10 failures? Do you think that when we got the 107 beads that were red, that's a good indication that we're going to have at least 10 red beads? Do you think that it's reasonable to think that we're going to have 10 non-red beads given the data that you just saw? Yeah. So we meet all the three conditions, so therefore we can go ahead and say we're going to use this formula. Confidence interval is equal to p hat plus or minus a critical value multiplied by the square root of p hat times 1 minus p over n. Some of you have this sheet. Let me pull this out. A lot of the details I'm going to go through are on the sheet as well. So you might want to have this sheet out while we're doing this. All right? So the rest of this slide is looking at, do we have normal? Okay. Here's another point. We make an assumption that all the p-hats that can be drawn out of that big barrel of beads, every single p-hat from every single sample of size 251, if you look at that distribution of sample p's, that it would be centered at p. That's another way of saying unbiased. And we achieve that kind of unbiased behavior by having a random sample. And that the standard deviation is what I had mentioned earlier. Okay? Now, here's where we're going to deviate from a formula. What's the difference between p and p hat?
P is the whole population.
P is the whole population, and p hat is a statistic. It comes from one draw. So when I drew those beads out of that barrel, do I know what p is? No, I don't.
You know statistically.
I know I got the draw, I got the statistic p, I got the p hat, but I don't know p. But wait a second. This formula says p, not p hat. We're screwed. We don't know what p is, so we can't use that formula.
Hold the day. I mean, this is.
Wait. Can't we just use p hat? It might be a little bit off. It might be.
Good.
But if we had to guess at what p was, is p hat a reasonable guess? It's reasonable. So you know what we're going to do? We're going to do a reasonable thing. We're going to cheat. Or we're going to use what we do know. We think p hat is a reasonable estimator of p, and we don't know what p is, so let's use p hat instead. And if you look at the sheet that I just passed out, this one, or that I said you should have out, you're actually going to see that that's exactly what we do. Okay. Ms. Simpson uses this notation. 1 minus p hat. She writes that as q hat. So on the sheet, no, because it's easier to write q hat than 1 minus p hat. So when you see q hat, it's really 1 minus p hat. All right. So we will use p hat instead of p because we don't know what p is. All right. So random, normal, and independent. We think we got all those conditions.
Well, is it P251? Oh, no, it's a simple.
No, that was 251 in this case is n, the size of the sample. All right, we've got the conditions all met. Let's do the calculation. What was our statistic? 0.426. What's the standard deviation of the statistic? Or at least our best guess. 0.426 multiplied by 0.574 divided by 251. I'm going to try, well, critical value then is what? It depends. It depends. Remember, there's a connection between confidence level and what you choose for your critical value. I need you to get your probability tables out for a second. In the previous chapter, I said 2 for 95% confidence. I said or around 2 or just about 2. Right? What's that? There's a table of critical values. Where is it? On page 17.
Oh my goodness.
It's 16.
Actually, the one I want you to look at is actually on 16. There's actually 2 tables of critical values. The one I want you to look at is on 16. All right, so everyone turn to page 16. And there's only one place on this table I want you to look. Okay, Rachel just kicked me in the knee.
Don't touch him.
All right. Okay, everyone got the table out because we're going to go through this, and you're going to make your life really easy. Are you ready? Look all the way down at the bottom. Let me just share that. Okay, all the way in the bottom on page 16, on what's referred to as often referred to as the T table. There is a listing on the bottom row that says confidence level. And then there's numbers just above it. Those are the numbers, the only numbers I'm interested in you using right now. So if I ask you, what is the critical value for 95% confidence? Now instead of saying 2, you're going to say 1.96. Now why is it not 2? Well, the 68, 95, 99, 7 rule is only approximation. Only the very bottom 2 rows. So 95% confidence, 1.96. 99% confidence, 2.576. 90% confidence, 1.645. Okay, so here is that lookup that you needed, gotcha. Okay, for the major kinds of confidence levels that you need, this table is where you go. Okay. I'm not going to explain what infinity means at this point. It's going to come up in the next section. Okay? But right now, just say the bottom row is where it's at. Michaela,
So just use the infinity row.
did you lose your table?
Yes, sir. But where do we know what number it is? We don't even know what number it is.
Imagine that Okay, can I just get a show of hands of people who need reprints of their tables?
I need this. I never got this.
Oh, okay, that formula, if you didn't get it, it should be in your hanging folder. For anyone who is absent, I put it in the hanging folder. Michaela, you need a new, the probability tables things? Okay, I don't have, I thought I had extras because I had, but I think what happened, oh, no, I do have. Okay, yellow or green? What? Yellow or green? I didn't put, I had them all printed out. All right. So, if you want to be, coming back to this problem, if you want to be 95% confident that you're going to capture, that your confidence interval is going to have in it the true proportion of red beads, use the critical value 1.96. Okay, now here's the, shouldn't be hard, but it often is. Please put it in your calculator right now. Tell me what the confidence interval is. Okay, I'm going to write down what Abby just said. 4.26 plus or minus 0.061. Okay, so she gave me the confidence interval in the form estimate plus or minus the margin of error. And that's a form that works. Okay? There's one other form that works as well. Okay, what happens when you take 0.426 and subtract it by 0.061? No, you get a number. 0.365, 0.365, and then we put a comma there. What happens when you take 0.461 and you add the margin of error? 0.487. Okay, so there's two ways to present the confidence interval. Point estimate plus or minus the margin of error, or the actual lower bound and the actual upper bound. We think, yes, Megan.
How do you know to use 95%?
Okay, it is going to be given to you as part of the problem. When they say construct the confidence interval, they will say construct a 95% confidence interval. Okay, here is the rule though. Here is the rule. If we don't tell you what confidence interval to calculate, 95 is the one to go with. It's the default confidence interval. Did you understand that? We will normally tell you what confidence interval to calculate by giving a percentage.
Is it usually going to be 95%?
If I don't give it to you, use 95% because it's the most typical.
I got this now.
Do you?
Ready to go.
Steam coming out of my ears?
Skin coming out of your ears.
Steam. Steam.
I don't know my skin coming out of your ears.
Okay. Okay. Now, I got to give one more piece of vocab. Jason was brilliant by saying instead of using P, let's use P-hat. Unfortunately, as soon as we use P-hat, that formula, that square root, is no longer the standard deviation of P-hat. It's not. It's a different. We're using a different number, so it's not the standard deviation of P-hat. So, to acknowledge that we are not using exactly the right formula, we're going to give the formula, the square root of P-hat times 1 minus P-hat over n. We're going to give it a different name. We're going to call it not the standard deviation of P-hat, we're going to call it the standard error. A slightly different name for a slightly different formula. No, it's life. But, you know, I'm not going to call something by its wrong name. When I use PAT, it's no longer that thing anymore. It's a new thing. What's that new thing's name? The standard error. All right. Ready for the next slide? So, when we use a statistic to calculate a standard deviation, instead of using a population parameter, we no longer have a standard deviation, we now have a standard error. So, this is, again, standard deviation of p hat. The standard error of p hat is the exact same formula except p hat's here. This is the standard deviation of x bar. Okay. So, to find the 95% confidence interval, we use a critical value. They said 2, we use 1.96. Using table A or a calculator, we can get more accurate critical answer. A calculator? What's that? How do we use the calculator to do this?
Go on the calculator app that Windows provides.
Stats. Test. Stats, test. And I'm going to go down this list. And there's this thing called a one prop Z interval. Which has got an amazing, amazing set of tools. It's a fill in the blank. Okay, let me fill in the blanks for you. X, how many successes did we have? What was it? 107 successes. Out of how many trials? What confidence level do you want? 95%? Can't put in 100. If you put in 100, know what the answer is?
Hey, where's that at?
Stat, test.
And alpha A.
Whoa, do those numbers look familiar? What is it doing? It's taking the numbers, it's calculating p hat, it's plugging them into the formula, and it's getting your lower bound and your upper bound. So, there are multiple ways to do these interval problems. This way gives you the confidence interval without actually having to go to the formula. Of course, I can write, and the publisher has written, questions that are dependent upon being familiar with the formula, so you should be familiar with both ways. It's very sweet. Took the 95%, it looked up the right the right critical value for you. It was excellent. All right. Now, one last thing on the vocab side. I've got this general expression called the critical value. And in the previous examples, we've been using 2 or a number around 2. We have a symbol for the critical value. and it's referred to as Z star. Z star. Yes, we have P hats and Z stars. It's a Z value because it comes from a normal distribution. It's not coming from a data point though, so we don't call it normal Z. Instead, we're saying it's a critical value, so we're going to call it Z star. So, Rachel, you asked the question, why does it say infinity on the bottom of that list? Would you do me a favor, right next to where it says infinity, on the bottom of the table that's on page 16, would you put next to the word infinity, would you just put the symbol Z star? And actually, in your book, that's exactly what they have on that line. They don't have infinity, they have Z star. All right? Is everyone okay with what we just did? All right. Now, what is the Z star value for an 80% confidence level? 1.282. Okay, so you can read it off that table. Now, I'm going to ask a very strange question. What is the Z star value for 75% confidence? No idea because that value doesn't exist on that last part of the table? It's true. Sorry, 75%. Okay. So, you don't take the average. There's a little bit of calculation that we do in order to find the Z star value for something that's not on that list. The most popular ones are on that list. All right? But if you get an oddball one, like 75%, you have to be able to find out what the Z star value is associated, even though it's not on the bottom of that table. Here's the methodology. 75% is the middle of a normal distribution. I have no idea what that is. Okay, so I would like you to recall that we are finishing on slide 9. And that's where we're going to pick up, we'll finish again, 8-2 tomorrow, quiz 8-1 afterwards. If you feel so moved, you can get started on 8-2 homework is posted. All right.